maybe 10 minutes or so to elaborate on a few more of the pieces related to the quantitative risk assessment activity that we did. And then I will pass the stage over to Alex Strauth, who is going to talk about design and assessment for dams and managing risk to major structures like dams. So in the activity that we did this morning, when we walked through the quantitative risk assessment equation, we provided some placeholder answers or inputs for the hazard probability term, the H term, and for the S term, the spatial impact probability term. And I think that we need to give you a little bit more information about how we come up with those terms and what's done in terms of hazard assessment. That's what we call that portion of the study, is the hazard assessment and hazard characterization. And to remind everyone of the definition of the hazard, the potential source of harm, that includes the process type, the size or intensity, and the likelihood of that hazard occurring. So, I'm gonna have to flip through just a couple slides to get to there we go. So for hazard assessment, the key principle that we use, sorry, I'm getting used to this mic. Does this work if I'm back here? Does that still pick up? Okay, cool. For hazard assessment, the key principle that we use for understanding hazard is this idea that the past is the key to the future. I'll put an asterisk on that related to climate change and get back to that in a minute. But for now, work with me, climate change aside. I promise I will get back to climate change. But generally, what we are saying for processes like floods, like debris flows, like rock falls, where the same type of event occurs over and over again in the same area, we can use what has happened in the past to understand what could happen in the future. And so what that means is we can study the existing geomorphology, the existing terrain and the shape of the terrain, and use that information to build our frequency magnitude relationships that we use in our quantitative risk assessments. Trying to decide if not, yeah. And then I mentioned that the asterisk, I'll wait on the climate change bit for now. So, how to, develop a frequency magnitude relationship. There's kind of maybe two types of frequency magnitude relationships that we might want to develop. You might want to do it at a specific site. And so that is asking the question for this community on a debris flow fan, maybe the same place where we did the assessment for the school this morning. What is the frequency and magnitude of hazards for this single site? In that case, we're going to look for clues of past events at that site. The other type of question you might be asking is regionally. What is the general frequency and magnitude of rock falls or debris flows along this road corridor, or within this province, or within this area? And in that case, you can look, same thing, look for clues of past events regionally, and then kind of adjust it to say, okay, I see that over this large area, we have debris flows every 10 years, and they tend to be one every 5 kilometers. So we're gonna do something like that. So there's some normalization. So really what we're asking everyone to do is to be a geohazard detective and to use all the clues that you have about what's happened in the past to figure out what could happen in the future. And that can include historical records of past events. In some places, that's documented in newspapers. In many communities, there is an awareness in the town. If you ask the people in the town, a grandfather will remember the debris flow that came down and hit his friend's house when he was 10 years old, and or that his school was closed for a few days when he was a child because of something happened. And so you can use that information. Now we can also use tools like satellite imagery or aerial imagery to identify and map past events. And then we can also map the landform. So having a sense of mapping the size of the fan or the colluvial cone. Sometimes you can even map deposits on that thing. And then the picture here is actually from a site near the Malamchi project. And this is a cut bank that the river made naturally. And so when you go to the field, you can look for sites like this, where the river has eroded down through the old sediments or through the fan, and you can use that to identify past events. And then you can often delineate them, so draw lines along them, based on, you'll be able to see maybe there's a finer grain deposit and then a coarser grain deposit, and you can figure out how thick they were and reconstruct from there. So these are all different tools that we would use, and what we would bring all these together to ultimately develop kind of frequency magnitude relationship. Any questions on that so far? Maybe one piece that I haven't explained is many of those techniques that I've just described, you can estimate maybe the area in plan view of a deposit, but then there are empirical relationships that you can use to turn that area estimate into a volume. So if you look in the literature, you can find tools to pull those types of things together. And then there are other tools that you can use depending on where you're working. If you have a site that has trees, sometimes you can use tools that date the trees or date the tree rings. That might be less relevant here. That's something we use in Canada. Sometimes you can use radiocarbon dating. But generally, this is enough to... And also another thing to remember is I think we as engineers need to avoid getting stuck in a trap of doing too much science. Because these kind of questions, a hazard assessment and understanding the frequency and magnitude of an event, you could do a PhD thesis on any single site to try to understand what happened in the past and what's going to happen. But at some point, when you're trying to use this information to make decisions, getting it exactly right doesn't matter. What matters mostly is getting a good enough picture to understand whether you need to manage 10,000 cubic meters of debris or 1,000,000 cubic meters of debris. If you need to manage 1,000 or 2,000, that's not that different. You need to know those big boundaries. So our caution in the hazard assessment stage is to just do enough to answer the questions that you have. All right. So that explains, and you can see my slides these are things. Go back. Okay, so that should give some initial understanding of how we come up with that H term, that hazard probability term. The other term in the risk equation that we looked at this morning is the spatial impact probability term, S. And then you also need to understand intensity. And intensity comes in the vulnerability term. So in the vulnerability term, you'll have a depth damage relationship that allows you to take a depth or an intensity or a velocity and turn it into a damage. So you also need to know what the flow depth is, velocity, intensity, to get that vulnerability piece. So we often get that from numerical runout modeling. There's many different numerical runout modeling tools. I have several favorite ones, but they are just my favorite because they're the ones I know how to use. So probably if you have one that you know how to use, that will work great. The main thing to make sure, regardless of which tool you're using, is that you understand the limitations of the tool, that you understand, for example, if the tool was developed for a certain type of river in Switzerland, you need to think about, okay, is my site similar to that, or is it different, and what do I need to change? So make sure you're using the right tools to actually answer the questions that you have. But then the numerical runout modeling tool can give you a sense of how far a certain event might go, and you might look at different scenarios there as well, and then as well the intensity. So hopefully that gives you a bit of an overview of where we get those H and S terms from, rather than just kind of making them up for a group activity. Any questions on that before I pass the floor to Alex, or any input, additions from Alex or Lauren that you'd want to make?
Maybe explain how
you can just make your life mine.
Explain how you get a probability out of the models.
That's actually kind of complicated.
Yeah.
Okay. Fair point. This is that's probably what we learned yesterday, right? Is that there was a bunch of things we were sharing that were actually really complicated, and we didn't give you enough detail. So let's give you the detail. To do that, I'm gonna stop this cast and try out my fancy dancy board again. Oh, but I lost my black. Okay. Ooh, trapped. Can I just be really loud? Does this work? Okay. It's fine for a couple minutes. Okay. So Alex raised the point of how we get from a runout model to a probability. The answer is, and it'll take me too long to put that thing on. It's complicated. The answer is that we talked about different hazard scenarios and how we look at different sizes and likelihoods. When we do runout modeling, we also often look at different scenarios. So in addition to modeling, oh, great, that's it. Hello?
That's good.
There we go. Okay, perfect. Thank you. So in addition to modeling, say, what did we have this morning? A 10,000 cubic meter event and a 20,000 cubic meter event. There is also often uncertainty on what that 10,000 cubic meter event will look like. I'm talking mostly about debris flows, but I can talk about this for landslides or for rockfall as well. It's all kind of the same thing. But that 10,000 cubic meter event could be a coarse-grained event that doesn't move very quickly and doesn't move very far, so that it has a certain rheology. The next 10,000 cubic meter event might have more clay in it. Maybe a different part of the watershed has failed, and the initial landslide that started the debris flow is different, and so there's a different rheology, a different flow behavior to that event. And so that event might move differently and go a different place. And then we might also look at different types of avulsion scenarios. So what that means is so I have a hazard scenario that say is a 10,000 cubic meter event, but then maybe I'm gonna look at two different rheologies. So there's a more mobile and a less mobile. And then maybe I'm going to look at a case where maybe my fan has a bridge. And maybe in one case, I say, okay, in this event, there's a lot of sediment aggregation, and the bed is going to build up, and the flow maybe goes out of the channel. Or in another case, I say, maybe the bed level is low, there's a lot of capacity in the channel, and the event is going to stay within the channel. So I'm going to look at two different it's kind of like the surface, let's just call it fan conditions. Oh, perfect. Okay, so I've got my, Look at me go. Getting so good at this thing. Okay. Okay, so we've got, in this case, we've got, this is for a single, oh dear, that didn't work. Okay, this is for a single hazard scenario with a certain volume. I'm actually going to run 4 different run-out models. And then I will give each of those run-out models a probability. So maybe I will say, and this part is often based on professional judgment about, or maybe it's based on, you did that mapping of the different deposits you've seen in the past, and maybe you saw that 70% of them were coarse-grained, and so they were less mobile, and 30% of them were fine-grained and had more clay, and they were more mobile. So you're going to assign that. And then you're going to do your different fan conditions where there's maybe more sediment and less sediment in the channel. And you can assign both of those a probability. And then we would run each of these different models and overlay them and give them weights. And so at a given house, you would say, okay, this house is hit by, maybe it's hit by this model and this model, but not this model or this model. And then you can calculate what the probability is of that site being hit. Is that the level of detail you were thinking of? Okay. Do you have an easier way? Okay, cool. Questions? Are you kind of coming along with me here? Would it help to walk through one of them, or should I? Maybe okay? If you want me to walk through, put your hand up. Otherwise, Alex is going to start talking. He's also very good. That'll be good, but... Okay. I didn't get any hands, so I'm going to assume that you generally follow this. Anything else you'd add? Any other questions? Great. Thanks, everyone.